I want to thank the organizers for putting together this great conference. So I'd like to tell you about some of our recent ideas for new ways to hopefully discover new fundamental physics experimentally. And actually, excitingly for me, I can even tell you now some very recent new experimental results along these lines. So my motivation, I want to discover new physics beyond the standard model. And it's getting harder and harder. I mean, colliders are an excellent way to go, but it's getting harder and harder, right? The next collider, I think, will unfortunately probably take decades. It's still very important to do. I mean, that's clearly a direction we should pursue. But that's a significant fraction of my remaining life. So I really think we need a new way. We need some additional ways to probe, to search for fundamental physics. I think at least one really promising direction is to look at small-scale, high-precision experiments. And sort of luckily, UV physics can naturally give us very light particles that can be possibly detectable in these very low-energy experiments, since pushing the energy frontier is rather challenging. And in fact, seeing these light particles can sometimes, as we've just been hearing, give us hints of really deep UV physics. In particular, specifically, I want to tell you about sort of three rather separate projects. The first is some new ideas we had on ways to look for, to detect Axion dark matter using NMR techniques. Then I'll spend a little bit of time telling you about some ideas we're working on right now to look for new hidden sectors, new gauge groups, new forces using electromagnetic resonators. And then finally, I want to tell you, just a little bit, advertise essentially a little bit at the end, some of our recent ideas for using cold atom technology to search directly for gravitational waves. And these are essentially three, disjoint topics. But they are sort of joined as being, part of the motivation for me is these cover kind of the, many of the generic classes of possible light particles that we could search for in these kind of experiments. In particular, if there's going to be a new light spin 0 particle, most naturally it should probably look like an axion. Spin 1 particles can naturally remain light thanks to symmetries. And of course, spin 2, surely the best motivated is the gravitational wave. And kind of a sort of unifying fact you'll see in all these experimental proposals is that I'm not really using standard classic particle physics techniques. So it's kind of better to think of all three of these as being very high phase space density. Think of them better thought of as fields, not as particles. That's sort of hand-waving intuition, but you'll see what I mean as I go along. And essentially, we're looking for the coherent effects of these fields on these detectors. OK, so to begin with, I want to tell you about our ideas for looking for axions. And I should say this has appeared in a few papers, and this is work done with, I'm a theorist, but this is work done with our experimental colleagues in Dmitry Budker's group, to whom we are very grateful for keeping us sane about what is possible experimentally. So the motivation, I'm strongly motivated by dark matter because dark matter is proof of physics beyond the standard model. It can't come from just the standard model. And in particular, I'd sort of like to qualitatively divide some of the most popular or most well-motivated dark matter candidates into two classes. There's what I would call heavy particles, of which the WIMP is sort of the canonical example. And then there's the class that I'm going to talk about today, which is really the light field class, and you'll see what I mean. And there, the axion is, of course, the best motivated example. For heavy particles, for WIMPs, we know how to look for them, right? We look for them, for example, we build a standard particle detector and look for the WIMP to come in and scatter and deposit some energy on a nucleus. Or you look for it in hard scattering at the LHC. All of these sort of share the similarity that we're looking for these single hard particle scatterings, these single interaction vertices. So the WIMP is really being thought of as a particle, and it's, say, depositing some energy in a detector or taking some energy away from an LHC collision. By contrast, the way I want to talk about looking for light fields is really to describe them as a classical field. Essentially, everything I'll be talking about will have a very high phase space density, which means instead of looking for these single hard particle scatterings, in fact, that would be impossible. The axion is way too light and way too weakly interacting. No way to do it with standard particle physics technology. You want to look for the coherent effects of the entire field acting together as a whole, not single particle scatterings. It'll become more clear what I mean by that as I go along. Now, of course, making this distinction between field and particle obviously is just hand-waving. You can describe it in either language you want. But at least for me, I found it to be really useful intuition in thinking of these ideas. OK, in particular, why can we think of it as, why is it best described as this coherent quantum state which looks roughly like classical field. Because all of these light fields, actually, the Axion has one example, but really it should happen for any light field, should be produced by the misalignment production mechanism, which really just means inflation, of course, produces a very homogeneous field initial condition for this field in the early universe. Then, since all of these fields are very weakly coupled as far as their cosmological history goes, they might as well be free massive fields. They begin to oscillate in their potential. And you know, then it's very simple to say what the state of the field is. It should just, well, it's basically a coherent state. It should be very well described by some classical VEV of a field, but of course, crucially oscillating with a frequency equal to the mass of the particle. Okay. Then it's a famous fact that field oscillating like this in its potential will clump like good cold dark matter. And in fact, that's one of the strong motivations for the Axion, that it naturally produces a very good dark matter candidate. Also, of course, for me, a very strong motivation is that it can arise very naturally, very generically from UV theories. It's very easy to produce Axions. And in the case of the QCD, I'll talk in general about all sorts of Axion types of particles, but in the case of the QCD Axion, that also solves the strong CP problem, so it's also very well motivated. Okay, so how do we currently search for the Axion? So I'm going to focus most specifically on the QCD Axion as the best example here. So the QCD Axion arises from Peccei-Quinn symmetry breaking at some high scale I'm going to call FA. So I plotted here, it's essentially a one-dimensional parameter space. The mass of the Axion and all couplings of the Axion are suppressed by that scale FA. And below about 10 to the 9 GeV or so, that's where these couplings are strongest, the Axion is ruled out by some combination of astrophysical and laboratory bounds. In fact, all laboratory experiments search for the Axion using this coupling of the Axion to electromagnetism, to photons. So F is the field strength of E and M. And you can see, of course, that down here it's relatively strongly coupled. So all these laser experiments, for example, can look for it. Anywhere, this is, by the way, I should say, a sort of crude theorist level cartoon. Anywhere above about 10 to the 11 GeV or so in F, the Axion can make up the dark matter, all of the dark matter. The one experiment that currently exists that can look for Axion dark matter, these microwave cavity experiments, or ADMX, they can look in this range of lower F, more strongly coupled Axions. The way that works, you have this resonant microwave cavity, you wait for your background Axion to come in, interact with your background magnetic field through this vertex, and produce some photon, or really produce a cavity excitation. Those experiments are fantastic experiments. This is my sort of rough guess as to the amount of parameter space they'll be able to cover. You can see why, though, they sit down here in this low F region, the lower F region. They're looking for this rate of Axion conversion. This amplitude is suppressed by 1 power of F. That means the rate is suppressed by 2 powers of F. So immediately becomes harder to go to the more weakly coupled Axions. That might be overcomable, but there's really a further problem, which is that this is a resonant experiment. The frequency of the cavity needs to be matched to the frequency of the Axion, the frequency of the dark matter. Which means, since the frequency of the cavity is set by the size of a cavity, that means roughly the size of the cavity needs to be equal to the Axion Compton wavelength. That's fine. So the mass of the Axion is suppressed by the scale F. In this range, Axion Compton wavelengths are something like this size. I mean, there's something like laboratory size. You can build a cavity that big. You can build a cavity matched to that frequency. But if you want to go up, let's say, to things motivated more by fundamental physics, if the scale FA from which the Axion arises is more like, say, the gut scale, 10 to the 16 GeV, then the Compton wavelength of the Axion is 300 meters. That means if you want to resonate with a cavity, you need to build an experiment that's 300 meters by 300 meters by 300 meters. That seems very challenging to me. I won't say it's impossible, but it seems very difficult, and I don't think we're going to do it anytime too soon. You could try to work on design your ways around that. And I spent a while trying to do that. But I think there's sort of a fundamental problem, which can sort of be said in the following way. This FF dual, that's a total derivative, which means I can integrate by parts, put that derivative on the Axion. That means any physical effect of that operator has to be proportional to the derivative of the Axion. In other words, that brings out the Axion mass, or if you like, 1 over the Axion wavelength. That means any physical effect of this has to be suppressed by the Axion wavelength. Another way to say it is a constant theta could have no physical effects. In practice, what that means is, at least I should say in my experience, and I think is essentially a theorem, any experiment you try to design using this coupling, which is a very valuable coupling. There's a reason people always use it to look for axions. It's easy to manipulate electric and magnetic fields in the lab. But any experiment you try to design using that coupling is going to be suppressed by the size of the experiment over the axion wavelength, usually squared. So that's fine down here, but it makes it a real problem looking at high F. All of your signals will be strongly suppressed. And it's really, you can see, a fairly general problem. I should say there were some ideas, for example, by Scott Thomas, that might be able to even push up this range with electromagnetic detection to some extent. But in general, you can see the motivating problem for me, I mean, why I got into this, what really worried me, was there's many orders of magnitude of parameter space here where it just looks very, very challenging. I mean, it seems like there may be no way to detect the axion if it's a dark matter and the F is at high scale. So for me, the question was, how do we go look for these high F axions? Can we do it? Or are we just screwed if they're the dark matter? And I should say the idea that got us very excited was to use a different operator. So remember, the axion was postulated as a solution to the strong CP problem, which is the problem that I can write this term theta GG dual in the Lagrangian. It's allowed by all symmetries, so it should be there, where G is the field strength of QCD, and theta is just some dimensionless parameter. And that does create a physical effect. That creates a small nucleon electric dipole moment proportional to theta. Of course, we're very good at looking for nucleon EDMs. So that rolls out theta down to a level of about 10 to the minus 9 or 10 currently. That's the strong CP problem. Why is theta so small? Why have we never detected it? To say it very crudely, the axion solves that problem by turning theta into this dynamical variable, the field A over F, which has dynamics that naturally drive it towards 0. So solving the strong CP problem. But of course, you can see sort of immediately just from those statements that since we're in the adiabatic regime, so long as the frequencies of the axion, the mass of the axion, are much less than the frequencies of QCD, the processes that are creating this nucleon EDM. In other words, so long as the mass of the axion is much less than lambda QCD, which it certainly is, then, as far as the nucleon is concerned, you're in the adiabatic regime, A over F might as well be a constant. It might as well just be a theta. So you know immediately you must create a nucleon EDM proportional to the local field value of the axion. Not some fundamental constant of nature now, just dependent on your local background axion field. Okay, what can you do with that? Well, we know what that background axion field looks like, right? We said it's basically described as a classical state oscillating with the frequency of the mass of the axion, roughly. We even know the mass of the QCD axion, up to this one parameter, it's set by lambda QCD squared over F. So very interestingly, if F is around the gut scale, for example, it's around megahertz, if you translate into frequency. Or in general, over that dark matter window of axion parameter space I showed you before, it's something like kilohertz to gigahertz, or 10 gigahertz. Those are very interesting frequency ranges. Those are ranges we can access in the lab. We can build things that have those frequencies to possibly detect this. So that's the first thing that makes you excited. And we even know the size of this field value, assuming, as you always do in direct detection, that the axion, let's say, in this case, makes up all of the dark matter. I know the energy density in the axion field is just m squared a squared in its potential, roughly. Crucially, though, because the mass of the axion goes like 1 over F, you can see this quantity goes proportional to a over F, the quantity squared. So that means, equating it to this local dark matter density, you can see that this quantity, a over F, although it's a very small number, is fixed, independent of F. That's crucial. In particular, what that means is we have a physical effect that does not decouple as all the couplings of the axion become weaker. To say it another way, this is a non-derivative operator. I mean, GG dual looks like a total derivative, right? But through the magic of QCD instantons, non-perturbative effects, this creates an actual physical measurable proportional just to theta, not to the derivative of theta. So you're not suppressed by the axion wavelength in this case. Also, this is a very cool experimental effect to look for, because essentially every single nucleon in the galaxy that's roaming around picks up an electric dipole moment, but it's not the normal kind of electric dipole moment. It's this rapidly oscillating EDM, oscillating at the fundamental fixed frequency set by particle physics, set by high energy physics, the mass of the axion. Crucially, that's independent of anything you put into your experiment. That's actually a key part of how we can possibly hope to avoid backgrounds. You always have to have some signal oscillating in your experiment so you can see it. Here, it's oscillating at a fixed frequency set by fundamental physics, not set by anything in your lab. Okay, so we considered many different ways of going to look for it. I'll just tell you about the one that seems most promising with current technology. And in particular, we want to look for this time-oscillating EDM. It's a very small effect, though. So we want to get every possible enhancement we can get. And a very nice, large dimensionless number is Avogadro's number. So we want to enhance our signal coherently, if we can, among a whole large material sample of spins. We want to use as many possible nucleons as we can. The best way, at least I should say the best way we found to do it, I think there might be many other great ideas. I think this coupling, this operator, has been not really explored up till now. But the best way we found to do it was to take a sample of spins. Now let me remind you, so I'll be using NMR technology, so let me just sort of very quickly remind you how NMR works in my crude theorist cartoon. Take a sample of spins, of nuclear spins, align them all, polarize them in one direction in the presence of some applied external magnetic field. By the way, as a technical but important point, the thermal relaxation time, known as T1 in NMR language, can be hours if you're at liquid helium 4 Kelvin temperatures. So that's crucial. That means that polarization lasts long enough for us to do the experiment. OK, so align all those magnetic dipoles, all those nuclear spins, then apply this perpendicular oscillating field, an NMR pulse. And you know, crucially, in a sense, the magic or the resonance of NMR happens when, think, time-dependent perturbation theory and quantum mechanics, when the frequency of this perturbation, so the addition to this Hamiltonian, B dot mu there, when the frequency of that perturbation, omega, equals the energy splitting between the two states, spin up and spin down. So when this 2 mu b external equals the frequency of the perturbation, that's when you have resonant spin flips. That's when you have resonant Rabi flopping. That's when you have a large effect on your spins in your sample. OK, sort of motivated by that, we modified it to look for the effect of the axion. So now we're looking for an electric dipole moment, d. So first of all, we should apply a perpendicular electric field, not a magnetic field. But in particular, there's a key difference, which actually is what makes this whole experiment at all plausible. This would not be a good experiment to look for static EDMs, and similarly, static EDM experiments are not good experiments to look for the axion. The difference is that this fundamental dipole moment is now oscillating in time at a fixed frequency set by particle physics. That means the resonance occurs, again, when the perturbation to this Hamiltonian, in this case d dot e, when the frequency of that perturbation, which is now the axion mass, equals the Larmor frequency, equals the difference in energy between spin up and spin down. OK. That means, unlike an NMR, we don't need to apply an oscillating field. We can just apply a static field, which is crucial. First of all, much easier to apply much bigger fields. Second of all, you're not flipping your field, your gigantic field that you've applied to your sample, at exactly the frequency you're hoping to detect a signal at. That's one of the big problems in looking for static EDMs and one of the things that creates large backgrounds. So we can just apply this static electric field and still achieve this resonant enhancement. OK, so there are a lot of experimental details. I just want to kind of very quickly tell you. When you're on this resonance, you'll get, of course, not spin flipping because the axion is a very small effect, but you'll get some non-trivial precession of all these spins coherently together. That creates, since it's a large spin density using Avogadro's number, that creates some transverse magnetic field that can be picked up in a squid, or in your best magnetometers. We consider it a squid. Now, there's a lot of experimental details I want to talk about, but they're crucial. For example, you want to use a ferroelectric to make this effective electric field as large as possible. So we considered lead titanate as one example, but actually probably some of the future work to be done is to think about all the different possible types of materials and which might be best. You need many different kinds of NMR pulse sequences, spin echo sequences, et cetera. I just want to mention one sort of crucial fact. There are many possible sources of noise in such an experiment. We've thought about them, and they all seem controllable. But crucially, the thing that sort of could have killed this is there's an irreducible noise just coming from any sample. Any sample has magnetization noise. Just some transverse magnetization. Actually, essentially from if you have a bunch of spins polarized up, and you're asking about the transverse magnetization, it's a quantum spin projection onto the perpendicular direction. That always has randomness in it, right? It's never perfectly 50-50. That always has noise. Crucially, you can estimate that, of course, roughly. Crucially, that noise seems small enough. Not much smaller than our sensitivity, but small enough to allow us to do the measurement. OK, so let me skip all those details. I'm happy to talk about it later and just show you where we think we can reach. So here's that axion parameter space again. We think this experiment is sensitive, actually, interestingly, to the highest Fs, the most weakly coupled axions. This is with current technology, things that have currently been demonstrated, though never altogether, of course. And I should say, this experiment has significant technological challenges. I think it's sort of like the early stages of WIMP detection. You still need to make significant progress, but Axions are very well motivated, and they deserve a similar effort. And there's really no other way to search for axions at this high F. And actually very exciting for me, just recently the Troms group in Berlin has some preliminary results, not quite getting down to the level of the QCD axion, but talking about general axion-like particles. And Dima Butker's group in Mainz is starting this experiment, starting construction now. And one of the reasons I'm so excited, this is not just, if a discovery in any of these experiments is not just a discovery of dark matter, it's also some glimpse into the physics at these very high scales, far beyond what any collider is going to reach. Okay. So much for the axion. Let me skip this actually in the interest of time, because I want to tell you about our ideas for looking for gravitational waves with cold atoms. And I should say, I just want to advertise this. Again, there are a lot of details, and they've appeared in several papers now. I'm happy to talk about them later. This is work done, crucially, with Mark Kasovich's experimental collaboration. So first, motivation, why look for gravity waves? I think really my motivation is they open this new window to the universe. Every time we've looked in a different frequency band of the electromagnetic spectrum, like microwave, for example, we learn a lot of interesting things. Here, gravitational waves are a totally different spectrum. They probably contain lots of interesting new information. In particular, we know white dwarfs, neutron stars, black holes, things that are very hard to see electromagnetically, are bright sources of gravitational waves. A black hole in spiral might be the only way to probe the near-horizon geometry of a black hole experimentally, for example. And of course, famously also, they're so weakly coupled they free fly to us straight from the early universe, meaning they are possibly the only way to directly observe things in the very early universe. Okay, so I, again, won't have time to talk about any of the details, but very roughly, the idea is we look for this using an atom interferometer. This is a space-time diagram of a single atom's path. What they do is with these coherent light pulses, split the atom's wave function, bring it apart, bring it back together, combine it, re-interfere, and measure the phase difference, measure that interference fringe in that end of the interferometer. That makes a very sensitive measure of anything that's different between these two arms. And in particular, less obvious is that it also makes a very sensitive measurement, relative measurement of what's happening to the atom versus what's happening to the laser pulses that are running, that are splitting this atom. So roughly, here's our idea for how to make a gravitational wave detector. You make a long common laser baseline. You want as much length as possible, since the effect of the gravitational wave scale is proportional to that. And you run these two simultaneous atom interferometers. And what they're really measuring is, as a gravitational wave passes through, it modulates, if you like, the timing, or it modulates the relative phase between the laser and the atoms, and between the two atoms. So very roughly, that's how you would build an atom gravity wave detector. And we think that with very reasonable parameters, sort of just beyond the level currently demonstrated, you could achieve, for example, in a satellite experiment, sensitivity comparable to the proposed LISA detector. And this would be, for example, with a baseline 5,000 times shorter. So certain technical requirements may be significantly eased. And certainly it's an exciting direction to go looking forward. I just want to point out one idea, a very recent idea that we had that we were very excited about. Every gravity wave detector, LIGO for example, has the problem, one of the main problems for gravitational wave detectors is laser phase noise. So LIGO, you could see the signal of a gravitational wave in just one arm of LIGO, but you have to use two arms because, of course, what you're seeing is shifts to the timing of the light travel time across the baseline. If the laser's not a perfect clock, which it isn't, it has some noise, you can never distinguish that from an imperfect laser. You can never see a gravitational wave. It's far too small a level. So you have to cancel it out along these two baselines. That's true with every laser interferometer-based gravitational wave detector. It would be true of the idea for an atomic gravitational wave detector I just showed you. But recently we had, and in fact I sort of thought that was a theorem, that there was no other way to do it. But recently we had a new idea. Again, I won't really tell you about this. Very crudely, here's sort of the space-time diagram of it. Very crudely, the idea is to use the atom more like a clock and less like an accelerometer. What you're measuring then are just how much time it takes the light pulse to go across. And you're actually not using the phase of the laser at all. You're not really using the fact that it's a laser at all. It could be sort of arbitrarily noisy, theoretically. This requires some different technology. So this requires using what are called clock atoms, things like strontium, instead of the things that are normally used for atom interferometry. This is something now they're working on because we've had this idea. They're now working actively on demonstrating this in Mark Kasovich's group. But crucially, what this would allow is single baseline detection. So here's sort of a mock-up of a satellite proposal we've been working on with our friends at NASA Goddard. One of the key things this means is you don't have to fly 3 satellites in formation, which is one of the things that our satellite engineer friends are very worried about, formation flying. So we think this proposal really greatly reduces technical risk and possible things that can go wrong, and potentially also cost. Okay, I just want to highlight some of the work that's going on experimentally. So this is in the basement of the Stanford Physics Building. They built this 10-meter tower, which serves as a test facility for all the technology we're talking about using cold atoms to detect gravitational waves. And just very recently, they've demonstrated actually some really exciting new results. So they finished construction on this a year ago, and they've now demonstrated almost a factor of 100 reduction in the coldest temperature people can achieve. So they're now down to tens of picokelvin, making this the coldest spot in the universe currently. They've also radically expanded, so this is actual data, I should say, and here's a picture of the atom's wave function at maximum splitting. So they've managed to make the atom have a macroscopic splitting of its wave function. That feeds in directly to the sensitivity. And also we have a collaborator, another group, Philippe Bouillet's group in France, who's got already a 1-kilometer tunnel, and he's working on demonstrating this kind of gravitational wave detector. Okay, so let me just conclude. We heard all about BICEP, and of course, we were very excited to hear about BICEP. I should say, if it's true, or if there are gravitational waves that are at close to the maximum level, R close to 0.1 or so, then I should say this is preliminary. This is something we're thinking about right now, but we believe close to that maximum level, we could see it. We could see those stochastic background of gravitational waves from inflation in these atomic gravitational wave detectors. A neat thing you can do is sort of in real time change from the kind of detector I described to one running in resonant mode. That may allow you to detect these at the sort of magic frequencies of 1 hertz. Just one of the many reasons that may be interesting is that you can see, of course, CMB looks at gravitational waves in these extremely low frequencies, right? Wavelengths the size of the universe, roughly. Here you'd be looking at the same gravitational waves, the same stochastic background from inflation, but at much shorter wavelengths. That potentially tells you, that CMB can only see the first few e-folds of inflation. That's looking many, many e-folds into inflation. That's looking well into the middle of inflation. You can test the scale invariance of the spectrum. You can even measure specific things about the potential. So I think that's one of the exciting ways forward. And in general, I think generally looking to directly detect gravitational waves will be a really important part of the future of astronomy, astrophysics, and cosmology. So, thank you.